thank you. Here's a quick outline of what I want to talk about. First, the point up at the top. I really love giving GVU Brown Bags, and more generally, internal talks on the campus of Georgia Tech. I've been here for 22 years, and I've done about maybe 10 or so of these. And each time, it's been a forcing function for me to gather thoughts about some newish idea and try to rally my own thoughts about it, organize them, but also gather people to kind of go forward in a particular direction. And it's been very successful for me. But usually what happens in the process is that, because most of you who know me know that I like to get things done well in advance, I typically do a dry run of a talk of a certain level of importance, and this certainly is a talk, being the GVU Brown Bag, of a certain level of importance. So I did a dry run of this talk a couple days ago, and it was horrible, which is a good sign, because you want the dress rehearsal to be really bad so that the show itself will be good. But it's usually made better because people give me feedback. And a lot of the reasons why I like to give talks about relatively new ideas early on is to engage people and give feedback. That's why what we do in an intellectual environment, we try to help people make their ideas better by challenging them or by encouraging them or whatever. So thank you, Keith and GVU, for giving me the chance again to speak. So what I'm going to talk about is highlighted here. I'm going to begin with talking about why more is less relevant, a discussion of Moore's Law and why I think there are limitations in the way Moore's Law has many of us think. I will then introduce a counter idea maybe to the Moore's Law thinking that I will call cosmos thinking, and I'll explain that, where less is more interesting and impactful. And this will introduce the notion of computational skin and the Cosmos project, and will culminate with the Cosmos conjecture, which is meant to be a little play on Moore's Law. Then I'm going to talk about the fact that Cosmos is in some sense a very grand and far-off vision, but you need to make steps to get there. So I'm going to talk a little bit about how we get from where we are today to that vision that I'm going to present for Cosmos. So I want to acknowledge some people who have had a lot to do with the development of these ideas. Not everyone who's influenced my ideas here on the campus of Georgia Tech is in this picture, but there are some people, some of you are here, and I'll give you a chance hopefully to acknowledge yourself. I can't resist saying this because I was just at a meeting where several people were expressing concern about the inability for people to have interdisciplinary research relationships here at Georgia Tech. And part of the problem might be because who's in our school and who's not in our school. I fundamentally disagree with that. But it's up to the individuals who want to collaborate with others. And I'm very fortunate to have a number of people here who are really enjoying, over the last 18 months or so, interacting with people who they know very little about. It's been fun, it's been slow, but it's been fun. So let me get on to the talk. So first part, more is less. Limits of Moore's Law thinking. What I like to do is to acknowledge people who have had influence on a large number of people. And this individual, Gordon Moore, clearly has had a lot of influence on the semiconductor and computing industry. He wrote, when he was working at Fairchild Research, before he founded Intel, he wrote a paper in 1965 that was based on some empirical observations of how the production of the basic computing elements, transistors and the like, were becoming better and better. The techniques for producing them were becoming better. And he observed through some empirical evidence, and essentially this is the graph from his original paper that he reproduced again in 1975 when he revisited this idea, demonstrated that because of the improvement in capabilities to manufacture transistors and other computing elements and integrating them onto a single circuit that could be manufactured, the phenomenon that resulted was that over time it would take less money to produce more and more compact representations of these circuits, these integrated circuits. This is what became known as Moore's Law. And one way to think about Moore's law, and the way I believe Gordon Moore intended it to be understood, was this phrase here. The number of transistors that you can buy with a certain amount of money will double every 1 to 2 years. Right? So that's kind of, when you talk to people who are hardcore computer architects, that's the Moore's law that they think of. But there was a reason why you could buy more transistors for the same amount of money, and it was the second thought here. This is a result of increasingly clever ways, and Moore said it, clever ways to manufacture integrated circuits at a lower cost with more and more components. So mixed into this is the notion that we could pack more and more computational elements into the same space over time. And as a result, things would be cheaper, but how we tend to interpret that is that we can get more and more power in less and less space. Okay, so that's Moore's law. So I have some good news, and I have some bad news with respect to Moore's law. Now, this morning at about 3 in the morning, I paid $12 to get this graphic, so you better laugh. Thank you. Okay. So I will start with the bad news. I'm sorry. The bad news is that Moore's law, as we know it, is over. And there's plenty of evidence that points to the fact that Moore's law is now obsolete. So if you look at this graph, the green line here is essentially how many people interpret what Moore's law was saying, that you'd be able to produce more and more transistors in some space over time. And that's effectively been following the doubling every year or two, which as you go on for 30 or 40 years becomes a very large number. But the other things that this graph shows are the evidence that it's not really the transistors that your grandparents knew. That's actually bad. Maybe that your older brother knew. So this purple line here is indicating that around 2002, we started to peak out in terms of the speed of the transistor. So we can pack more and more transistors into the same space, but they're not any better than their predecessors. And so their performance is not getting any better, though we can pack a lot of them. The other graphs in here show things about the power consumption and other issues. But basically, we can pack more and more transistors, but they're not better and better transistors. And prior to about 2002 or so, not only could we pack more and more transistors, the transistors themselves were better. So computing was getting better on a variety. And there's a longer story behind that I actually have been educated on the last 18 months. But I'm not going to educate you on that. Maybe at some later time. But in addition, there are some more kind of, shall we say, political statements that have demonstrated to us that Moore's law is obsolete. There is this Semiconductor Research Alliance that produced, and I use the past tense now, something called the Technology Roadmap for Semiconductors, which was basically saying how Moore's law was going to progress for the next 2, 5, 10 years. They decided this year that they're no longer going to produce that. And in fact, they don't think that you're going to be able to get down to feature size, which is one of the critical elements of a transistor. You're going to get much below 5 nanometers anytime soon. So they're saying that interpretation of Moore's law, it's not going to happen, so we're not going to publish this report anymore. Now, what company did Gordon Moore found? Intel. Funny enough, this year, Intel said that they're abandoning the principle of Moore's law. So I think that's a pretty profound statement. It's trying to manage expectations of the world, saying you're not going to get in 12 years the same size thing that's going to be faster and cost the same amount of money. That's not going to happen. So we don't follow that anymore. But if you also think about what I said was the actual Moore's law about the cost of transistors, it's actually been the case since about 3 or 4 years ago that we no longer are even able to produce transistors more cost effectively. So all aspects of Moore's law seem to be coming to an end. Now remember, Moore's law was just a statement of an empirical finding. So it wasn't some theory that was put forth. And so the evidence, the empirical evidence is pointing to an obvious end to this. And many organizations have claimed this. So I'm not telling you anything new. The new part is going to come later in the talk. So more important that this empirical evidence of the size and cost of transistors is changing or is ending in the way it's been is how we have interpreted Moore's law. And by we, I mean a lot of the people in this room who are those who build and invent interactive technologies that involve a lot of the computing capabilities. So here's what I will call Moore's law thinking. Computers will always get smaller and more powerful. You may not think that you operate under that assumption, but let me demonstrate you empirical evidence that we very much operate under that assumption. Here is a picture of augmented reality in 1997. Now, I didn't have enough money to buy the picture of Blair McIntyre wearing these things, but this was Blair's world in the late 90s when he was at Columbia doing some of the first people to do augmented reality. And it should be fairly obvious to you that this person isn't wearing a backpack to carry books around campus. That backpack and all the other stuff that's wrapped around them is to enable the headset to do the very minimal augmented reality that they wanted to be able to demonstrate in 1997. Here's Moore's law thinking. That is augmented reality today. We went from this to that in 20 years. Moore's law worked. All that crap that this guy had to wear went away. And now it's something that not only can do the augmented reality, but it can do a whole bunch of other things. Right? So I can understand why we do Moore's law thinking, because it has worked. And so here's what happens when we try to digest Moore's law thinking as academics. Student comes to advisor and says, here's my prototype. Doesn't run in real time. It's a bit bulky. But the idea for the future, it's there. I'm sure of it. Here's my video. So the advisor says, that's okay. Moore's law will take care of your problems in a couple years. This is not your problem to worry about. Go ahead and publish it. That's Moore's law thinking. That is going away. We can't say in 2 years. So here's my current example. I have two current examples. Here's my iPhone 7, right? Pull out your iPhone 6S, your iPhone 6, and your iPhone 5, and this is not twice as powerful in many dimensions. It's certainly not smaller. It's definitely not cheaper, but that's a different issue. This is my brand new MacBook Retina Pro, which looks, feels, weighs, and performs exactly like my 3-year-old MacBook Retina Pro. So we're out of that era of, in 1 or 2 years, I'm going to get a faster, more powerful machine. So that's the bad news. Now, the good news. Right, we're going to have 4 years of really good late-night television. I can guarantee you that, right? But that really was not the point. I don't know who put those images in. The good news is that Moore's law is finally over. So that gets us to the second part of the talk. Less is more, by which I mean more interesting and more impactful. If we think in terms of what I will describe to you as computational skin, and what I'll present is the cosmos conjecture. So to start this, I'm going to talk about a second influential idea. You're all fairly familiar with this individual, Mark Weiser, and his article written in 1991, "The most profound technologies are those that disappear. They weave themselves into the fabric of everyday life until they are indistinguishable from it." What's resulted from that since 1991 is that we have technology in a variety of different sizes. Weiser introduced the notion of thinking about inch-scale devices and foot-scale devices and yard-scale devices, but we've gone beyond that, right? We can now think of building-scale technologies, and we have what we now call this Internet of Things, which is a whole bunch of devices all around the world that are connected. But all of these devices are manufactured via silicon-based integrated circuit technology, which is what Moore's Law was all about. I think we're in a very interesting era now where we can think about building computers a different way. So one way we can make computers differently today is we can print computational capabilities onto existing pretty much everyday material, plastics, paper. So we happen to have one of the world's best at doing printed electronics here at Georgia Tech in the School of Electrical and Computer Engineering, Professor Manos Tantzeris. His Athena group has done a variety of examples of how you can get computational capabilities by printing with, in some cases, very standard off-the-shelf inkjet printing capabilities. What's shown down here in the bottom is just one example they've done in their lab where printing on cardboard or paper material, you can print an antenna that harvests energy to power a printed sensor that can measure soil moisture and then communicate information some distance. Put it in the ground next to a plant and you have something that's a self-sustaining soil moisture device, monitoring device. That's a different way to think about building computers. So that's what's inspired, that and some other things have inspired this goal that we have of producing what I'll define for you as computational skin. And just remind you that this was kind of literally presaged by Weiser when he said they weave themselves into the fabric of everyday things until they're indistinguishable from it. So a computational skin is a material that will do a number of things. It'll store information, it'll compute logical calculations, it'll sense, take input from the world, it'll actuate, do things that signal to the outside world or manipulate the outside world. It'll communicate within itself as a skin and between skins. More interestingly, it's self-sustaining from a power perspective. So it'll harvest its own power to do those previous operations. It's manufactured in large quantities to obtain a low cost. That's a little reminiscent of what Moore was talking about. And it'll do interesting things. So that's a computational skin. There are some examples we can think about. So here, I'll talk a little later in the talk, is an image of a prototype element of an RFID that's fully printed, that's done as a collaboration between material scientists here and Manos Tantzeris' lab. But you might envision that we'd be able to get to the point where these skins can be manufactured or easily placed upon any existing material. So this is a concept image that Dinjin Zhang and some of his friends had produced to try to give an idea of, well, where might you find and use computational skins? So that's a little bit of the vision. Now, the title for this section of the talk was Less is More, as opposed to More is Less. More is less, powerful. Less is more, impactful. Why less is more? These computational skins I'm talking about as a standalone computer are not very impressive. That's the less part. They don't do that much. But the mass provisioning of these computational skins everywhere, that is very powerful. That's the more. So it involves thinking about the deployment of simpler, more ubiquitous computing materials in an environment to achieve a greater goal than you might with this ever-increasing, smaller, more powerful computer that Moore's law thinking has you do. Okay, so that is the idea behind computational skin. So how do we get from where we are today to this vision of being able to produce skins that you can place on any physical object or materials that are objects themselves that will have these computational capabilities? Enter the Cosmos project. I'll give you a hint if you don't already know. Clever name, not Gregory's invention. So computational skin, my invention, probably not as clever as it needs to be. Cosmos, damn clever. Computational skins for multifunctional objects and systems, Cosmos. And we're trialing a logo up there in the right-hand corner. Do you have your little audience reaction meters? Because we've been, I've got Hillary's old staff in the back there measuring the response to this. But what I'll point out to you here is that this is a combination of a variety of different disciplines. We have people from material science, that's Eric Vogel in the top here. We have people from chemical engineering, or it's called chemical and biomolecular engineering here at Georgia Tech. They're about manufacturing things, Michael Filler. Electrical engineering, so Manos from ECE. We have, in the College of Computing, there are many interesting different disciplines. We have computer architects, Tom Conti and Hadi Esmilzada. We have people like myself who do human-computer interaction. What we're missing, and what this talk is meant to be a call for, is enough designers. And I'll hopefully give you some motivation for why that design is needed. So that's the Cosmos project. But that's not enough, right? Cosmos thinking. What is Cosmos thinking? This is Cosmos thinking. Computers can do better things by covering more area. What was Moore's law thinking? Computers are always going to get smaller and more powerful. Okay? You can think it that way if you want, or you can think this way, or you can think both ways. But this is computers can do better things by covering more area, by being more present in the physical world. So, how do we get from where we are today, which is this world with silicon-based IC chips all over the place, to a world of computational skin everywhere? One way you can do it is by printing computation on things that already exist. And I talked a little bit about Manos Lab doing this kind of work. To go a little further, we need to be able to do manufacturing of materials that at the point of manufacture they have the computational capability. So I'm going to call that non-silicon computational fabric. Where is Felix? Felix, using your fabric here. It's probably a better name than computational skin, but I wasn't able to give up yet. So there's the acknowledgement. So in Cosmos thinking, the student comes and says, here's my prototype. Doesn't work over this whole building. And it's a bit slow to produce, but the idea for the future is there. Then the advisor said, that's okay. We know that the Cosmos conjecture will take care of that. Publish it. Let me give you some examples. So this is some work done by a number of people, but Dinchen is the main lead. There are a number of other people doing this. The idea behind this Cosmos sticker is that it's an inkjet printed, so fully printed, fully passive touchscreen extension. What's the motivation? We have a lot of touch screens these days, right? Phones, watches. Sometimes we put the touch screen inside something else and we can't get at the touch screen, but that's a touch screen device that's in there, so we might want to do something to put the touch outside. So what if you could produce a simple material that could extend the touch screen for the phone, or extend the touch screen for the watch, or create access to the touch screen for this cardboard VR device by putting it outside? That's the simple motivation. Can you take touch screen capabilities and move them somewhere else, but still direct them to the original touch screen? There might be a variety of reasons you'd like that. I think the VR one's a really good example, but you might want, when playing a game, to interact on the back of this screen. It's kind of expensive to put another capacitive screen on the back of this phone. But what if you could have a cheap material that essentially transferred the touch that you expect to do on the front to the back of the phone? That's the motivation. How do you do that? Well, it turns out, in some sense, I don't mean to diss you at all, Dinshin, but this is remarkably simple and easy if you think about it. I didn't pull up mine. Anyone here ever used a pen to write on their touchscreen? How is that pen working? You have the pen, yes, but you know how it works. I didn't ask to give me the pen, but I will take that. Thank you. So how does this pen work? Right? So this pen extends the capacitive feature of the screen off the screen by conducting the relevant features of your skin or your being to this point here. So I've essentially moved it off the screen. Okay? That's about $7, right? Yeah. So you really wouldn't miss it. Okay. Take that simple idea and now lay a series of tracks on a film, a thin plastic film. And you can provide the ability to touch in this area or touch in this area, and you conduct the paths of your touching up here along some sketched lines to some other region. And place these regions on the side of the phone, and now it's as if you're touching the side of the phone or anywhere you place this on the phone. You've essentially done the same thing that pen does, you've just made it a little more complicated. So all good ideas, if described well, which I might not have done, seem obvious in retrospect. So kudos to Dinshin for coming up with a very simple idea that does something that hadn't been done this way before. Here's a little demo of what you can do. There's no sound to this, so I'll do. So you can extend the touch. You can put touch where you don't have it before. What's he doing? Playing Fruit Ninja. You can interact on some other part off the watch that might be bigger. You can look even more foolish with Google Glass. So that's one idea. Very simple idea. We'll come back to look at whether that gets us toward the vision of Cosmos in a little bit. I'm going to talk a little more briefly about this other example. This one is technically more complex, and it's not complete yet. But I assume many of you are familiar with RFID. Here's an example of a near-field version of RFID that we have on our phones that allows us to pay, sometimes a little more easily. Right here is a schematic of an RFID tag. This is a passive RFID tag, which means it doesn't need to be powered. It doesn't need to be powered by a battery source. It's powered by the radio frequency emission that come to it from an RFID reader. What's important about this graphic is that for a while now, we've been able to print the antenna. But this part of the RFID tag, which you don't really need to know much about electronics to figure out that there are many more boxes there with many more labels, so it's probably doing a lot more of the job, right? That part here is built using traditional silicon-based IC technology. So the question is, can you get to the point where all of this could be printed? Take a piece of paper, stick it in an inkjet printer, and out comes an RFID tag. Fully passive, fully working RFID tag. So we're not there yet, but the first step toward that, or one potential first step, is to be able to build the little components that make up these pieces of the IC technology. One of the pieces that's very relevant for power management as part of the energy harvesting is a diode. So one of the basic building blocks. So the first thing that Eric Vogel and Manos Tentzeris and their postdoc Spiros are working on is, can you provide a way to fully print a diode? I'm not going to go into any details of this except to show that is a schematic of how they actually can today print onto paper. This down here is this piece of paper, and these are all things that are printed. And you can see it's actually three-dimensional, so there's several layers that are done. So a particular kind of diode, a Schottky diode. Many more details I can give you if you want, or I could probably better point you to people that can explain those details much more competently than I can. But there's two examples I've given you. A fully printed, fully passive touchscreen extender, and a fully printed piece, important piece, of an RFID tag. So now, we're starting around second, heading into third. You guys get we're past baseball season, but I figured you're okay with that, those baseball analogies. Go Cubs. The Cosmos Conjecture. Why you came, because you got to come to a talk that's got an alliterative title, don't you? I have some, if we have time, I have some outtakes at the end of the talk of alternative titles for this talk to see, when I give it again, what might be a better title. But before we get to that Cosmos Conjecture, I want to build you a little bit of a story But one of the features of computational skin is that you're able to manufacture it at a fast rate for low cost. So let's address manufacturing rate. Now these are figures here are compliments of my colleague Mike Filler in chemical engineering, chemical and biomolecular engineering. If you look at the annual production of silicon-based integrated circuits in the world today, roughly around 3 square miles are produced every year. That doesn't seem like an awful lot, does it? Or at least doesn't seem like an awful lot of area. Certainly isn't going to cover all of Atlanta. Certainly isn't even going to cover all of Georgia Tech. If we look at some other technologies, like a flat panel display, if you look at the annual production of flat panel displays, you get up a little bit more, about 65 square miles. Okay, so you're covering Atlanta, maybe, with that. If we just look at flat glass, things that cover all the buildings, that's up to about 2,000 square miles a year are produced. Okay, that's a lot more. But if you think about the coatings we put on things like paint, wallpaper, plasterboard, that's produced at a rate of about 130,000 square miles a year. Okay, so just look at the gap between annual production rate for silicon wafers and coatings. If we're thinking in terms of the cosmos world, we need to get computers to be like this if we want them to cover all objects. We need to get production rates that are that fast. So for cosmos thinking, production at the rate of the coatings, not going to be done with the silicon wafer technology. So what is the cosmos conjecture? The cosmos conjecture is, don't worry. The global annual area produced of these computationally enhanced materials, computational skin, is going to double every 2 years. And what that means is if we start in 2016 with about the rate for silicon, which was the 3 square miles, in a mere 20 years, we're able to mass produce at the level to cover buildings. So that's the cosmos conjecture. Notice, very important, yes, it's alliterative, okay, but it's conjecture. It's not law. I don't have any empirical evidence to base this on. It is an aspiration. So let's take a look at the two examples I showed you before. The Cosmos sticker. Well, how does it do as a piece of computational skin? Does it store information? Does it compute logical information? Nope. Does it sense? Yeah. Touch your finger on it, knows the finger's touching. Does it actuate? Not really. It just passes that signal along. Does it communicate? Absolutely. I put that skin on top of another skin, which is your touch screen, and it communicated information. Is it self-sustainable from the perspective of power? Yes. Fully passive. Doesn't need any power to work. Nice. How was it manufactured? Well, Dinchin did this. It took him takes him about 9 hours to produce a piece of this touch screen that is roughly 4 square inches or 10 centimeters by 10 centimeters. So it's 100 centimeters squared in 9 hours, which, I did the math for you this morning, is roughly 100,000 square centimeters per year. That's the production rate, which is not a lot. I didn't get a cost for him, but this is not that expensive. I think you could probably produce this, I'm going to guess, for a couple dollars. You got some silver nanoparticle ink, you've got the acetate, the capital cost of the inkjet printing, that we're just going to accrue that over 1,000 years, so that's nothing. Right? So it didn't cost an awful lot, but it was kind of slow. The other thing was computational skin has to do something interesting, so I had to generate my own empirically validated scale of interestingness, and decided, like most scales that are empirically validated, it needs to go from 1 to 10. 1 is the lowest, not at all interesting. 10 is the highest, extremely, extremely interesting. And I think this one's about a 4. It's interesting. It could be much more interesting. But it's not uninteresting. It does something useful. Let's take a look at the Schottky diode. Store information? No. Compute logical information? Not really. It's just a diode. It says whether something can pass through or not. Does it sense? Well, kind of. Scott will take me to the side, and Peter will take me to the side and say, I have no understanding of sensing. Does it actuate? Well, it does change its state, kind of, and let things go through, so that's a little bit. Does it communicate? Not really. Self-sustainable power? Yes. You print the antenna, it harvests the power, it does everything. It needs power to operate, it harvests the power to do it when it's integrated with the printed antenna. How's it manufactured? Fully printed. Rate and price unknown, which you could probably assume is very slow and pretty expensive. Is it interesting? Well, I think to most people in this audience, they would say no. But if we say to Peter, being able to fully print a working diode, is that interesting to you? Yeah. So we average the two, and we get a 7, right? Can I borrow your little pointer? Thanks, Peter. Okay, so those are 2 examples. And so that's showing that we've got some things that we can start to do. And the way we think about getting to the ultimate vision in Cosmos is by producing fully printable solutions. The folks in material science and chemical engineering are much more interested in producing materials that will have these abilities from the very beginning. They're working on that. I think that's a few years out before they can start to produce things at this rate, at this capability, but it's coming. This is really interesting to me. Okay, so now I want to conclude. Resist being dominated by Moore's law thinking. Don't always think that computers are going to get smaller and more powerful, because they're not going to continue to get smaller and more powerful. Embrace the ways of the cosmos. Think that computers can do better things by covering more area. But in retrospect, Cosmos and this Cosmos conjecture are actually pretty faithful to the spirit of both Moore and Weiser. Moore's law was about more and cheaper computational elements, ultimately printing and mass-scale manufacturing with, so for example, producing an integrated circuit without photolithography, which is what the chemical engineers want to be able to do. That's the way you produce things at large scale cheaply. So it really is about making the computational elements cheaper and faster. So it's kind of consistent with Moore's law. So maybe in 10 years I'll come back and say, Cosmos conjecture, Moore's law, we actually extended it for another 20 years, you're welcome. I won't have done it, but I'll take credit. And Weiser, weaving into the fabric of everyday life, he meant that figuratively, but I think we actually are at a point where we can think about doing this literally. And what will it mean if we can produce any surface that can have some computational capability and can be in contact with many other surfaces and do interesting things? So I'm going to stop there, and I'm going to ask you for any questions you might have. But I just want to make this one point, I'll get right to you, Irfan, that so I hope that someone in this room remembers this 15 years from now, because that will have been a successful accomplishment. But don't come back to me in 15 years and say, oh, you were so wrong about computational skin because the doubling rate was 18 months, not 2 years, you idiot, right? Okay, to which I will say, remember, I said, it's not that this vision needs to be necessarily accurate. It just needs to be something that inspires people. Okay, so questions. Irfan.
Why does this vision limit itself to just a touch sensor that's going to be in the whole world?
Oh, no, I'm sorry if you got the feeling that I was only thinking about touch sensing. Computational skin is a variety of sensing and actuation capabilities. I didn't have time, but in my undergraduate class this semester, it's the Intro to HCI. Are there any folks from that class? I see one person from that class. The others are getting extra credit by, I told them that it's going to be recorded. Is it recording going to be available for them to watch? You can turn it off because that would so screw them, right? And you're the only one who gets the extra credit. So they were given this task this semester of think of any object, any everyday object, understand its uses, and look for opportunities for what it might do if it had computational skin-like abilities. And you'll attest to the fact that this talk is hardly reminiscent of the talk I gave you to motivate what computational skin is. It's probably, I don't know if it's better or worse, you can tell me, but it's different. But I tried to motivate them with the idea of what computational skin might be. they've come up with a number of very interesting ideas, but one of the consistent ideas that they have, and Caleb and Felix are TAs in that class, is this idea that they want computational skin. They're taking it very literally, and they're also influenced by what we know already. There's a project on backpacks that wants the backpack itself, when you're on a bike, to automatically light up and be your light, so they want that to be actuated. When you buy a pair of shoes, if it's comfortable, you don't necessarily want to buy a whole bunch of different, well, you're fine, you might want to buy a whole bunch of different shoes, but really what you want is a pair of shoes that will match your outfit. I'm showing you an example of one that does not, just to get the point across. You'd like to be able to point to some pattern or point to what you're wearing and have the skin of your shoes automatically adapt to that color. Those are the kind of ideas that these undergraduates who are taught some design and interactive design principles, that when they get the idea of computational skin, that's how they think about manifesting it. And it's much more than just transferring a simple kind of touch sensing. Yes?
So a lot of this computation that you talk about is external, but
What do you mean by external?
that it's outside of us as human beings. But we're also
Oh.
moving in this direction where a lot of the neurological implantation of computation within us, making us actually,
Yes. So, so two comments to that. Absolutely. I think that's another direction that one can go. That's not necessarily what I'm talking about. But what a lot of people think of when you say computational skin is they think this skin. And I initially was, oh, no, I don't mean that kind of organic skin. I mean these kind of surfaces. But why don't I mean this kind of skin? Maybe I do mean this kind of skin as well. But what you were talking about, I think, is another potential direction. We'll call that the Ramic reminiscence, reflection, the Ramic reflection, what might be in the future, consumable computing
So
devices.
thinking in the direction that let's just not do any of the computation outside, let's not change the code outside, let's just change it in everybody's brain, the fact that they see the thing.
Well, okay, so as usual, when you ask a question, it brings up lots of ideas, and I will answer something that's probably not at all related to your question. But that's the privilege I have standing up here. The brain, and is Nivedita here? I saw her. There are a lot of people for many years that have been looking at being inspired ways to do computing by how humans do computing. And one of the biggest advantages of understanding how the human brain works is that it's an incredibly complex computational machine and it consumes very little power. So this is really interesting if we think about wanting to produce self-sustaining computational capabilities. We can't harvest lots of energy, at least currently. So we need to do things with very low power. So there is a whole branch in Cosmos and elsewhere thinking about what's called neuromorphic architectures. That's where the computer science folks are very interested. Very low power ways to do what the brain does, and what the brain basically does is a lot of pattern recognition. So what are pattern recognition tasks you can do at low power with relatively simple circuit design? I didn't have enough time. That would have been the third example I would have given here of where we're going. So great question, terrible answer, but that's the way it goes.
So, I mean, I noticed that the Schottky diode that you had molybdenum and sulfur and other things, and they're hoping that they can figure out ways to print that in a traditional inkjet printer. But is the aim for this things that can be printed in an inkjet printer, or like big, large factories?
No. So the inkjet printer is just the first step. It's a I mean, and it's part of the reason why it takes 9 hours to produce is because they're not particularly fast. What is fast is roll-to-roll printing and roll-to-roll manufacturing. So if you can do things on flexible surfaces, then you have a chance of being able to do very high-rate production. But certainly an inkjet printer wouldn't do that.
So what are the environmental implications for these materials? Can they be recycled, managed?
That's an absolutely wonderful question, and I have a whole bunch of slides I decided not to put in here. One of them is talking about the opportunity and the obligation that computational skin represents. Where is this device most likely going to be in 3 years? In a trash heap in India. All right, no, in Africa, sorry, most likely. Right? We produce a lot of computational cycles, and we do not at all recycle them, because we believe that it's okay to get rid of these ever smaller, ever more powerful computational devices. That table will probably be here for 20 years. If I'm going to empower that with computational capabilities, maybe I'm going to be in a world where I can literally take the skin off and upgrade it with a new skin, but not likely. And if I'm actually producing the wood or the pulp and making that computational, I'm not going to be getting rid of that anytime soon. So this is nice because it will force us to think about doing things and having them last for a very long time. This is another problem with Moore's law thinking, is that we tend not to worry about being very efficient with computation, because in 18 months, we won't have to worry about being efficient, and people throw away their old computers and get new ones. So this is an opportunity, but a challenge that comes, that now the cycles aren't going to go away because the cycles are part of the material itself.
You're cursing us with furniture that's not going to speak the current version of iOS?
That's possibly true, but we'll talk about language in a different talk. Yes, Caitlin.
Just your idea about the table being around and being a computational device brings up the thought, this is just a thought, about who's going to really want to go into making a table as a venture. The return on investment in making furniture in addition to computational things is going to be really low. It's going to be really complicated. And so I think if there would be development in that area, people would want to make it more technical and less bulky and less confounding with other kind of elements, like you need a furniture designer, you need a woodworker. I don't think there would be many ventures in that area. It wouldn't be a very profitable venture, I think.
That's right, because there are not many companies that make furniture. Right, there are not many companies. So your point is well taken. Here are two comments I have about that. I believe that we are on the cusp of an alternative computing industry being established. And the question is, who are going to be the leaders of that computing industry, the alternative computing industry? I think there are at least three choices. One, it's the Intels of the world who say, well, we're going to have to start making computers differently. I think that's highly unlikely to happen in the next 5 to 10 years because they're very resistant to giving up the massive investment that they've made in silicon-based IC manufacturing. Another option is an entrepreneur like yourself who might essentially produce the next Cosmos. Let's call it Kugel, that will produce computational skin and find some niche initial adopters and then go spread throughout the world. Another alternative, which I think is possibly most likely, is that it will be the Procter & Gamble's of the world. The companies that are already in the business of mass manufacture of everyday goods. And they'll say, oh, we can now manufacture these things at a reasonable cost, and they can do more than just sit on your counter and emit toothpaste.
Yeah, I think along those lines, you see kind of the difference. While there's not a lot of folks that make furniture, there's a lot of people who make soft goods. And so I think that that's a really logical place for Cosmos to happen, is in our tablecloths, in our curtains, in our textiles.
Yes?
So the thing about RFIDs is they just sit there passively unless they're powered by something
Yes.
that does emit radios. How do like if you integrate sensors into a wall, say, how do they?
What a wonderful question. Did I leave that slide in here? Maybe didn't. Okay, so this is another project we're looking at. Yeah, here it is. I hid it. I'm not going to show it. So let's imagine a piece of paper that could harvest enough energy to do a simple counting or a simple communication of a piece of information. That's what RFID does. Or a simple taking in of a piece of information. So let's take counting, because that's essentially, I'll take in that there's something near me, and I'm going to increment a counter. What might one do with something like that? Let me give you a very simple scenario. I rip off a Post-it note, and I write a note on it saying, I'll be back in 20 minutes. And I put it on my door, and I leave my door. Haley comes with her Bluetooth phone, comes near the door, reads the sign, and leaves. Goes away. And then Jung-Wook comes, reads the sign. He's also got his Bluetooth phone. And he leaves. Now, there's a lot of ambient RF in the environment that you could use to harvest energy. There's also additional bursts when a Bluetooth device comes nearby. Can you harvest enough energy from that ambient and this changing ambient RF to allow this piece of paper to count the number of times a device owned by an individual came nearby, so that the next time Gregory comes and takes off the phone, it communicates to him, 7 people came by your door? Okay? maybe that's a 3.5 on the Mellish meter. What do we call that? Interesting nature. But those kinds of capabilities and a piece of paper, that piece of paper with simple kind of neuromorphic pattern recognition with pressure sensors might be able to actually recognize me writing on it and communicate that information to the wall, the door, when I put it on it. The door is connected to a hinge, is connected to a wall, is connected to an outlet, is connected to the internet, so the message can go out. Right? That's, I think, the interesting thing and why I say here, break away from our past measures of success. My colleagues likely will disagree with me on this, and I don't mean these colleagues, because you all adamantly agree with everything I say. It's the people who are not here will disagree with me that one of the problems, like with wireless computing, is that the measure of success for wireless computing is we need to blast more information a longer distance. So that's how they measure. Oh, mine's better because it blasts more faster. Well, but if we've got things that are always coming in contact with each other, we don't have to blast much over a very long distance. So we don't need to have that kind of measure of success for this kind of wireless or between-skin communication. These things, I think, are possible if we change what our measures of success are for these computing capabilities. Before we get to these other talks, I have to absolutely share this with you. I had some ideas for alternate titles for this talk, and I need your advice. Where did I put them? There we go. So, you know that the people in this, on this project are Eric Vogel, Mike Filler, Tom Conti, Manos Tenzeris, Gregory Abowd. So here were some different ideas I had for the title for this talk, and I just want to, because I'm not sure the Cosmos Conjecture really gets all the ideas across. So I want your opinions on these different alternative titles. I decided to go with the Cosmos Conjecture because of the alliteration. You might be wondering what I thought. So Eric Vogel, well actually Manos Tenzeris, because I talked about his work, right? His is about print it and they will come. That's the Tenzeris tautology. He's all about printing electronics. Print it and it'll come. Eric Vogel is all about nanotechnology and materials. So his tagline is, you know the expression, it's just a matter of time? His is, it's the matter of time. So, and the Filler fact, Mike Filler is the chemical biomolecular engineer. He's the guy about manufacturing things a lot. And he always talks about being able to produce this mole of nanoscale transistors that he hands to Manos that he puts into an ink and then spreads all over the place. I'm not sure, but that's the Filler fact of life, is that you'll be able to produce a mole of transistors. The Abowd abomination is just about anything that comes out of my mouth. And the Conti conundrum is that if it's not neuromorphic, it's not interesting. Okay, so you can give me any of the comments there. And now I'll take any other questions or, yes, go on.
Assuming we achieve production feasibility, what are the biggest challenges you foresee in large scale adoption?
Assuming we get what?
Like production feasibility, like,
Oh, okay, well, I think the two biggest challenges in what I present is being able to harvest the power to do what the computation is going to want it to do, and the mass manufacturing. So you gave me one of them for free. So there's only one answer. It's making sure when you manufacture these things, they can harvest the power they want. Now, what Tom Conti likes to point out is many things, particularly if they stay put, probably aren't that far from a power source. Maybe, but that table isn't that far to power. So this wall is pretty close to a power source. So I think the two big challenges, well, actually there are three big challenges. It's harvesting power so that you can do what the computation wants, which is part of the reason why the first examples of computational skin aren't going to do a lot, because there's not going to be a lot of power to do anything with. Manufacturing it at mass scale. And one of the projects I didn't talk about here is trying to buck the trend of doing large-scale integration manufacture using photolithography as ways of being able to trace where the elements should be placed. So doing this mass-scale manufacture without photolithography. There's a lot of good reasons why you'd want to do it, but it's really hard. And the last one is doing things that people care about, right? I think there's only so many billions Dinshin's going to make by that touchscreen thing, and then it'll end, okay? There have to be compelling uses for these technologies. And that's why, how this Cosmos project started is, I'll get to you guys, sorry. You may think I'm a really creative guy, but I wasn't. Eric Vogel and Mike Filler came to me and said, this is where we think, what we'll be able to do in the next 5 years. Would anyone care? I said, that question, would anyone care, is really what I would like to think about. And I don't think I'm actually that good at answering that question, but designers are really good at doing that kind of work. There were 2 hands over here. Okay, yeah. What's your name, young man?
Alex.
How long you been a student here, Alex?
A couple years. For the students in the room who are interested in prototyping some of the things that the skin is one day going to be able to do you think it's a reasonable expectation to say, stick a iPad onto the wall and prototype some interfaces, functionality, use cases like that? Or are you envisioning a different kind of sort of interactive environment and visual environment altogether?
It depends what their goal is. So certainly for the students in my undergraduate HCI class, that's a perfectly reasonable way to prototype the experience so you can get reactions from people to understand, is that the kind of world you'd want? For someone like Dinchin, a PhD student, a researcher, that's not going to pass muster in his research community. So he's going to have to produce something that doesn't look like an iPad. And unfortunately right now there's very little you can do that's fully printed. So initially what you're going to have to do is print mostly and then tack on the integrated circuits and hope that they're really small, low profile, low form factor. This is a really fun game. Pick any video from the UbiComp or WIST conference of the last 5 years and try to trace where the power cord is. They cleverly film things so that you don't see that, where all the work actually happens. Right? So that's going to be a challenge for people going forward. But if you're just wanting to get at the user experience, and, in some sense, you don't even need the iPad. If you can sketch the ideas appropriately and brainstorm and get reactions from people, often that's very valuable to get feedback about, oh, that's a horrible idea. Or, yeah, I could see that being interesting. But for us, fully printed, once you look at the fully printed, said, can you manufacture that with your chemical engineering techniques? Can we get away from having to have the material and then print? That's the direction that's really interesting. That's what I think is the 5, 10, 15, 20-year goal. Scott, did you have your hand up?
I didn't have a question, I had a comment.
Uh-oh.
Can you run back, what was it, a dozen slides or so to your...
No, I cannot. This new laptop, they disabled the back feature in PowerPoint. But, okay, so how many
your table of production volumes.
Oh, okay. What's wrong?
No, that's great. But it occurred to me that we are making, note card size things that do have smarts in them. They often look a lot like...
Yes, absolutely.
And I wanted to know if I could find any production numbers on that. So I willingly ignored the 10 minutes of your talk to beat my head against Google.
And you found?
It appears that somewhere on the order of 2 square miles of RFID cards were shipped to China in 2011. I'm sure that's gone up since then.
Right, so it sits somewhere between silicon wafers and flat panel displays, sounds like?
Yeah, and the fact that we were already there 5, 6 years ago. Wow. Okay.
Okay, take Scott's advice. Tile the world with buzz cards. And Cosmos is a done deal. Take your millions of dollars and go.
I mean, some of this is rolled to run manufacturing.
Yeah, absolutely, absolutely.
They do a surprising amount of computation on them, so it's interesting there are other corners of industry doing it.
Yep. The thing that can't do is you can't put a buzz card on top of another buzz card and accomplish something.
Howard's hard.
Yeah. Kayla, you had your only one more. Can you guys talk? Well, can you guys confer and turn your questions into one? No? Okay, sorry.
Did you get the first word?
Go.
So one of these things that it was I was thinking about, especially after the question about sustainability, was that in terms of printing on everything, space isn't usually a concern, which is often why we try and get to smaller, things, right, electronically. But if you're going to print on a table, it's not going to be difficult to put an IC in the table, right? And then have the printed stuff on top. So in terms of our environmental kind of impact, if table manufacturers are like, oh, we can do this skin, but then we're going to print I don't know how many tables are in this,
Yeah.
30 tables worth of ICs.
I get you.
That'd be a lot.
Right. Okay. So this is where you're right. And I think now particularly in the case of power harvesting, it's going to be hard. But the thing that you have an advantage of is you have large surface area. So the trick for harvesting power is to have lots of surface area or wampin big antennas. right? Not something the size of that credit card, right? A table surface is much bigger, probably has much more opportunity to harvest. So what we have to do to encourage those manufacturers not to do that is we have to show them how to do the efficient harvesting in an environment like this, which has, you know, a little bit of light. It has RF. It has mechanical things, like when I do things like this, I can produce power as well. That's it. Thank you very much. Any feedback you got, please give it to us.